Welcome. This recording is related to week 10's lecture of the course Insurance Risk Models. In this recording I am commenting the proof that the Bühlmann, the estimator for the premium in the Bühlmann model is the best linear Bayes estimator with respect to the quadratic loss. So what we are looking for is an estimator of that form. So we want we want our premium to be a sum of a linear combination of past experience plus a constant. So we want to minimize the quadratic loss, which is with respect to the loss of next year, and that's this expression. We want to minimize it. So natural approach is to look at the first order conditions. So with respect to our parameters, so the alphas and the constant b. So let's look first at the first t partial derivatives of this expected value with respect to the alphas. So if you take the derivative of this, you have a 2 going in front of it, and you multiply by the coefficient of alpha, which is k, when you are taking the partial derivative with respect to the alpha k. So you have this expression, and you want it to be equal to 0. You can reorganize this because now, the square has disappeared, as 2 times the 2 can be dropped, and you have the expected value of alpha times the product of the x's plus the expected value of b times the x minus the expected value of x times the x of next year. So you have a minus, so you put it on the other side of the equality. Now if you take the derivative with respect to b, you have almost the same, but there's no coefficient in front of b, so you get this expression. Again, if you distribute the expected value in that expression, you get this equation. So what we do is we take this first equation minus the expected value of xk times this equation. So you see you have this minus this times the expected value of xk. This will be the sum of alpha covariance of xt with xk. And then we have b expected value of xk minus b the expected value of xk. So this disappears. And then we have the expected value of xt plus 1. Oops. Let me use another color. The expected value of xt plus 1 times the expected value of xk minus the product of the expected value of xt plus 1 times the expected value of xk. And this by definition is the covariance of xt plus 1 with xk. We have t equations here, a system of t equations. So what we get now is a system of t equation again. So if we want to we can express this system of t equations with matrices. So you'll have alpha 1 times the covariance of x1 with xk, and then alpha 1 x2 with xk, and so on. So you have a big matrix of the variance covariances, xt xk times vector of the alphas equal to the vector of the covariances of each of the x's with the x of next year. Now we need to look at this covariance. The covariance of these x's unconditionally is not zero. Okay, the x's when the theta is not given are positively correlated. But you can expand this covariance with the covariance rule as the expected value of the conditional covariance plus the covariance of the conditional expected values. So the conditional covariance is zero, but only if I is different from k. Because of course, if I is equal to k, well, it's not I, rather here it's t. If these are the same, then you have the variance of x given theta. So the variance of x given theta is sigma square of theta. So just keep that in mind for the moment. And then you have the covariance of the conditional means. The conditional mean of xt and xk is the same. It's mu of theta. So this covariance, the covariance of a random variable with itself, is the variance. So we have the variance of mu of theta, which leads us to two cases. If I is equal to k, in this here you have the covariance of xt with xt given theta. So that's the variance of x given theta, which is by definition x sigma square of theta, plus the variance of mu of theta. By definition, these are our parameters s square and a. Now, if I is different from k, this is 0, and we still have the variance of mu of theta, which is equal to a. So you can rewrite these matrices as the matrix of the variance covariances. The variances are s squared plus a, and all the covariances are equal to a. And here you have the covariance with each of the x's with the one of next year, and that's a again. If you look closely at that, at this system, you can conclude that all the alphas must be equal. Because in the first line you have t minus 1 times alpha 1 times a plus s squared plus a times alpha 1. And this is equal to a. So in other words, each of these lines are equal. But in each line you change the coefficient of a different alpha. So the only way for this system here to have equal lines is for the alphas to be equal. So we will call this alpha, this constant alpha, as alpha tilde. And this alpha tilde, you can solve it, it's a over s squared plus t times a. And that's 1 over t plus s squared over a. And s squared over a was our definition of k. So this alpha tilde is 1 over t plus k. That's what I told you in the lecture. So the credibility premium will be the sum of this alpha tilde times the x's plus the constant. So it's t times the alpha tilde times the mean, because remember that the mean is the sum of the x's over t. So here we have the sum of the x's times the constant. So the sum of the x's is t times x bar. So we are just replacing the sum of the x's by t x bar. So t alpha tilde is t over t plus k, the z of the Bühlmann model. We still need to determine b, and we'll do that by requesting that the unconditional mean, or the unconditional expected value of our premium formula without any experience, or unconditional, should be equal to m. So it's kind of unbiased condition, and you get from that b is 1 minus z times m, and that's the end of the proof.